Hi everyone. So today we have a very interesting question in calculus, and many times we've seen how symmetry can help us in number theory, combinatorics, algebra. But actually, symmetry can be very useful in almost all areas of mathematics, including integration. So yeah, we have a really nice question, and let's just get into it. So this is problem number B1 from the Putnam exam in 1987. And in this video, we're going to talk about how we can maybe exploit symmetry in definite integrals. Then we have a very important result, or rather an idea or a problem solving technique that you should keep in mind when doing definite integrals. Then we have some book sessions of college mathematics, and at the end, a simulable challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so the question is telling us to evaluate this integral. Now, when you look at this, there is no direct symmetry that you can see, other than the fact that you have this ln root 9 minus x in the numerator and the denominator. But again, there's not much that you can do with this right up front, and it does look a little bit intimidating as well, right? So maybe before we jump into this, let me kind of draw attention towards the general framework, okay, or a general idea of how we can, tackle these kind of problems. So let's say we have an integral I, and that integral is such that we need to integrate f of x divided by f of x plus f of k minus x dx, and it's a definite integral, so limits are from a to k minus a, right? Okay, great. So this is in a way a general integral, right, in terms of the function f. So the question is, what is the value of I? Does this I have any particular value in terms of k and a? Because k and a will obviously be constants, right? So if I can find out I in terms of k and a, that'll be great. What's the symmetry over here? Like, what is the catch? Well, the catch is that if you check out the sum of the lower and the upper limit, basically the sum of the limits is basically k, right? Then you have this x over here, you have this k minus x over here. This is also, kind of summing to k. So this is kind of the symmetry that is involved. And when you have when you have a case like this, you can very easily evaluate such kind of integrals. And evaluate by just simple u substitution, right? So you take u is equal to k minus x. So du therefore becomes negative dx. And then we maybe figure out the limits. When x tends to a, u would tend to k minus a. And when x would tend to k minus a, which is the upper limit, u would then tend to a. And here, consequently, x just becomes k minus u, right? Just reversing the order. So okay, if I just write the integral in terms of u, I get I is equal to integral of f of k minus u du with a negative sign divided by f of k minus u plus f of u, and the limits from k minus a to a. Now, if I just swap these limits, I'll have to multiply by negative. So this just becomes integral from a to k minus a, right? F of k minus u du divided by f of k minus u plus f of u. And again, definite integrals does not depend upon the variable of choice. Therefore, I can write this as f of k minus x dx divided by f of k minus x plus f of x. Basically replacing u with x, right? Okay, great. And okay, let's just maybe call this as equation number 1, what we had to find essentially. And let me just call this as equation number 2. Now, if you just observe, if I just add both of these equations, 1 and 2, basically 1 plus 2, this is what I'm doing. If I just add these two equations, I'll get f of x plus f of k minus x in the numerator and the same term in the denominator, right? Which is great because they just simply cancel out, and then we are just left with nothing but the integral of dx, which is nothing but x from a to k minus a. So 2i just becomes k minus 2a. So I just becomes k minus 2a by 2. So this is great because we cannot now have an idea, right? So the complex looking integral that I had written above, which is I, the integral from a to k minus a of f of x divided by f of x plus f of k minus x dx simply turns out to be k minus 2a by 2, right? Okay, this is great. Now let's come on to the question, right? So in the question we had to evaluate this integral, and let me actually just call that j, right? So j is basically integral from 2 to 4 of the natural logarithm of 9 minus x divided by ln root 9 minus x plus ln root x plus 3, right? And we need to kind of evaluate this. Okay, very fascinating. Now, if j is basically a form of I, that would be amazing, right? Because you already know the result of I. So if j is kind of using the similar format as I, this lower limit is a, so a needs to be 2, right? And similarly, the upper limit was k minus a. So here also k minus a needs to be 4. So k minus a needs to be 4, or since a is 2, k just becomes 6. So we know the lower limits and the upper limits over here, right? Okay, great. Then in the numerator, we had this function f of x. So if I just maybe let f of x equals to square root of 9 minus x, or rather with the natural logarithm square root of 9 minus x, what would be f of k minus x? F of k minus x would be nothing, f of 6 minus x, right? So I can just write this as ln square root of 9 minus 6 minus x, right? So f of k minus x or f of 6 minus x just becomes ln root 3 plus x. Oh, that's great, because ln root 3 plus x is this. So this is f of x, this is f of x, and this is f of k minus x. So it is basically the form of I, right? J is basically just I with f of x as ln square root of 9 minus x, right? And with we know the limits as well, right? So the value of j will be nothing but k minus 2a by 2, right? With k as 6 and a as 2. So j then just effectively becomes 6 minus 4 divided by 2, which is 1. So the value of this integral so happens to be 1. So we kind of knew, in a way, because we knew this format for I, we could solve it for j, because it so just happens that j solves this general format. So j is in a way a case of the general format where the function is ln root 9 minus x, right? And the lower and upper limits are known to us, so we could find out the numerical value of j. But let's say if you did not know this, then you would have to use a very crazy substitution idea. So if you actually remember, while calculating I, what substitution did we use? We used the substitution u is equal to k minus x, right? U is equal to k minus x. Now it so happens that here, in this function, in this integral j, u is equal to k minus x. So you would have to use a u substitution of 6 minus x, because k was 6. And when you look at this, the number 6 does not resonate anywhere in the integrand. 6 is the sum of limits. That's the only connection. So, but yeah, that was if you can think of that substitution in the exam, I think that's a pretty good substitution, right? Otherwise, I think this general framework is really beautiful, and I think it's something that can be remembered, or like the technique to solve it can be remembered for future applications as well. So yeah, the entire result or the major takeaway from the video is that the general framework, the value of I, or how to solve an integral of the form of I, is what we should keep in mind. So yeah, hope you learned something from that. Okay, so we have some book sessions of college mathematics: Introduction to Analysis, Principles of Mathematical Analysis by Rudin, Calculus Volume 1 and Volume 2 by Apostle, Topology, Contemporary Abstract Algebra by Galian, Topics in Algebra by Herstein, Abstract Algebra by and Foote, and Linear Algebra done right by Axler. Okay, so at the end of the same level challenging problem, now again, you need to use the general framework of I. If I were to just remind you, I was nothing but the integral from a to k minus a of f of x divided by f of x plus f of k minus x dx is equal to k minus 2a by 2. Right? Essentially, this is just a general framework that we kind of need to remember, that the integrand may be of the form of this. And there's a possibility the integrand might look like this, with certain given function f of x. And this is what you need to exploit. So, kind of solve this integral, you just have to do the u substitution k minus x. And then after that, it's just addition, and then it's pretty easy to find out the value. So yeah, this given integral, I'll just give you a hint. It is of the form I, but you just need to figure out how exactly you're going to apply it. So maybe try it out. It's a pretty simple question, and let me know if you are able to solve it. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.